Hey there everybody, in this video we are going to be talking about how to evaluate trig limits. So limits involving trigonomic functions, sine, cosine, tangent. Just as a heads up, we will not be going through the proofs as to why these limits are evaluated the way they are. We will briefly discuss that in class, but just for the purpose of this video, it's purely going to be plowing through the math. Now, let's talk about evaluating limits. We've already seen a few videos on this. First thing we always want to try to do is see if we can plug in our variable. If we can evaluate it straight out, we're going to do that. Otherwise, we might have to factor, conjugate, simplify somehow, or we might have a scenario in which we have an asymptote. Another way to evaluate limits is by looking at a graph. And to start off today, we're actually going to take a look at some graphs of trig functions to get limits. All right. First one we're going to do is sine of x over x, and we want the limit as x approaches 0. Now, if we tried directly substituting in, I can't plug 0 in for x because I'd have a 0 down in the denominator here, but sine of 0 is also 0, so I have 0 over 0, which means somehow, some way, some shape or form, things might cancel out or simplify. There's really nothing for me to factor here. I can't conjugate because these are both just monomials, single terms. There's no complex fractions going on. So all of my techniques that I've used previously are kind of out the window. So we could take a look at a graph here. This is the function sine of x over x. So we have a little bump right up here where x is 0, and then we oscillate just kind of back and forth up and below the x-axis. We can see that our function is not defined at 0. However, the limit from the left side is the same as the limit from the right side, so the overall limit does exist, and that's going to be 1. Now, you could always verify this if you wanted to on your TI calculator. I have the instructions here. You could plug that into your y1. You could set the zoom to a trig function. You could try evaluating using the trace function at 0, and you would get an error, which is just your calculator's way of saying that that function is undefined at 0. But we could kind of focus in on what's happening as we approach 0, and we see that we get that 1 value there. Another trig function that we're going to see is tangent of x over x, limit as x goes to 0. And we have the exact same thing here. We have our limit existing on the left and right-hand side, however, the function itself is undefined. So even though our function is undefined, we still have a limit that exists, and that limit happens to be 1. The third and final trig limit that we'll discuss today is 1 minus cosine of x over x. 1 minus cosine of x over x as x approaches 0. And this one is going to vary slightly different than the other two. Instead of approaching 1, this one actually approaches 0. So let's generalize these. We have the following trig limits. They're all limit as x approaches 0. The first two are essentially the same concept. One's got a sine, one's got a tan. A is just any generic coefficient. One thing to make note of is this ax is inside of the sine function, inside of the tangent function. That is the argument. It's not sine times ax. It is sine of a times x. But within all of these, what we're seeing is that if the coefficient on that argument for x matches the coefficient on x in the denominator, we get a scenario in which this whole thing approaches 1. Same exact thing goes for the tangent. Once we get into the cosine, you'll notice the a's are kind of gone. And the reason why the a's are gone is this numerator is no longer just a monomial. We'd have two separate terms. So that denominator of x affects more than just itself. So this 1 minus cosine of x all over x is kind of on its own separate island there. If you need to, I would strongly advise pausing the video and making sure you have these written down here. Because what we are going to do is we're going to add some pattern recognition to our arsenal. So anytime we're evaluating limit with trig functions, we can pick apart any of these patterns and evaluate accordingly. Another thing to note, when we are solving these, it looks like we are going to substitute this out in place of a 1. Mathematically, that's essentially what we're going to be doing, but behind the scenes, there's a lot more stuff going on. We have an entire function who is approaching 1, so it's not a direct substitution for 1. So it's important that I make that known. Okay. First one, we have the limit as x approaches 0, sine of 3x over x. Well, this one would be very convenient. It would be very nice if down here, if this was a 3x, not just plain old x. So if I had a 3x right there, then this whole thing would just equal 1. Well, that would be super convenient. The issue is I can't just change the value. What I can do, though, is I can be sneaky about how I do this, and I can multiply this fraction by 3 over 3. 3 over 3 is just a fraction whose value is 1. I haven't changed anything now, I've just changed the appearance. So now what I have is I have that 3 down in the denominator, and now I have this 3 that's chilling up in the numerator here. And I know that the limit as x approaches 0 of sine of x over 3x, that approaches 1. So this limit evaluates to 3 times some function that approaches 1, so this overall limit will approach 3. So all I did is just some simple algebraic manipulation there. All right, next up, limit as x approaches 0 of 2 times tangent of 4x over sine of 5x. Woof. I'm seeing a tangent of 4x. I would love it if there was a 4x underneath there, because then my argument would match that denominator. Unfortunately, that's not the case. Well, let's make it the case. I'm going to multiply 4x over 4x to this numerator. That's really just technically multiplying by a value of 1. Down below, I'm going to do a similar thing. I'm going to multiply by 5x over 5x. Now here's what's going to happen, is I have tangent of 4x over 4x right here. That will approach 1. I have sine of 5x over 5x right here. That will approach 1. So now as I'm evaluating this limit, what I really have as the limit as x approaches 0 of 2, this tan x over 4x approaches a 1, so I don't really need to worry about it. So I've got 2 times, I still have that residual 4x left over right here, over 5x. Again, I still have this residual 5x over here. Now I can't just directly plug in 0 because I'd get 0 over 0. However, these x's would negate each other. So I have 2 times 4 all over 5. This thing evaluates to 8/5. All right, next problem. We have 3 sine of x over sine of 5x. All right, similar as before. My argument here is a 1x. I would love it if there's a 1x underneath there. Here my argument is a 5x. It would be so great if there's a 5x underneath. So let's force that into existence. I'm going to multiply this top by x over x, because now I get that sine of x over x that I wanted, which approaches 1. Down below, I'm going to multiply by 5x over 5x. Because what that does is it gives me a sine of 5x over 5x, which approaches 1. So we're going to evaluate this limit now. As the limit as x approaches 0, we have the 3. That sine of x over x just approached 1, so I don't need to write it, times x, the residual x from the top, over, we had just a plain old 1, times that residual 5x right there, I can't plug in 0 directly because those x's would screw things up. I'd get 0 over 0. However, they do negate one another. My final evaluation here is 3/5. All right, I know that kind of seems funky. But these are problems where the more you see, the better you'll get at them. You know the drill, folks. If you have any questions, do not hesitate to ask. And as always, good luck, have fun, be safe, roll tide.